This is review video 33 about heat and heat transfer. First, let's define heat. I talked about it in the last video about energy, but heat is specifically defined as a transfer of energy between a reaction system and its surroundings. Or alternatively, that transfer could be between two different reaction systems. But again, heat is not a static thing. It is a transfer of energy moving from one place to another. Specifically, we are going to represent heat with the letter Q, or the variable Q, and whenever we represent heat, 9 times out of 10, the units for it are going to be joules. There are a couple of others that you could see for heat, but most of the time, again, it's going to be joules, or you'll need to convert it to joules to work with it mathematically. Heat can be transferred between a system and its surroundings in a couple of different ways. The first one, the most obvious, is conduction. So conduction is heat transfer through physical touch, right? So in the diagram over here of this person holding a very hot pot full of water, there's conduction happening between the heat that's traveling through the handle of the pot here and it's going towards this person's hand. So I'm sure we've all touched something hot before and we've let it go really quickly going, oh my God, that's so hot. That's because the heat is transferred to you through physical touch or conduction. Molecules can transfer heat through physical contact as well. We know that a faster moving molecule can knock into another one and then cause that molecule to speed up its movement as well. That's how heat transfers through solid objects. That's how heat transfers through liquids or gases, etc. Now, the second way heat can be transferred is through convection. So convection is heat transfer through the movement of a fluid. And I don't want you to think that a fluid is only ever a liquid. It could be a liquid or a gas as well, because gases can be defined as fluids. But basically, if you have a heat source, say down here at the bottom where I'm drawing in yellow, the movement of those fluid molecules are going to touch other molecules and heat them up, and then the movement of those liquid molecules, in the case of this pot, are going to scooch throughout that liquid, heating up the whole thing as those molecules continue to move around. This and conduction are similar at times, yes, because technically the molecules have to touch each other to transfer this heat between them, but convection is a subtype of a conduction heat transfer, where that heat is transferring through a fluid, not a solid, or not through direct physical contact between two separate entities. We're all in molecules of the same sample here. Radiation is the last type that I want to talk about. Radiation is heat transfer through electromagnetic radiation, or electromagnetic waves specifically. So an example of that would be our sun emits a lot of EMR. It emits light, it emits so many other things, and through that emission heats our planet over the course of a lot of distance, right? The sun is millions of miles away, but it's able to heat our planet through that EMR traveling. Fire specifically, down here, as we can see in the photo, fire is going to emit a couple of different types of EMR. The visible light we can see, but visible light doesn't tend to transfer a lot of heat energy with it, but the other thing that fire emits is infrared radiation. And so when you sit near a fire, the reason you feel that heat is because that infrared radiation is hitting you, and it is transferring energy from the fire to you specifically. So how does heat move from one place to another? Well, first of all, always, there are no exceptions to this. I know it's the first time I've ever said this, but heat is always going to move from a hotter place to a colder place. And you can kind of think about that as the same principle as the diffusion of molecules, if you've learned the principles of diffusion before. Molecules always move from an area of really high concentration where they're really close together, and they tend to spread out naturally or move to an area of low concentration. Heat works the same way. Hot places have a lot of energy, so that area of high concentration. Cold areas do not have a lot of energy, so heat is naturally going to spread to those cold areas. As we already know, when heat flows into a reaction system, we have an endothermic process taking place. Similar to our delta H value, our Q value is also going to be positive when heat is flowing into a reaction system. As a consequence of that, the surroundings are going to feel cold. So an example of that you've probably used at some point is one of those cold packs. You break it, you shake it up, and it gets really cold. The reason it gets cold for you is because you are the surroundings of that reaction system, and that reaction system is drawing energy from you into itself, making you more cold. When heat flows out of a reaction system, Q, again similar to our delta H value, is going to be negative. We have an exothermic process going on, and our surroundings are going to feel hot. So your example for that is fire. We've all been around a fire before. We've all felt its heat. But what's happening in that combustion reaction for fire is that that reaction is emitting a lot of energy. Energy is coming out of it, making you warm as the reaction system itself gets cooler over time. In terms of defining a reaction system and defining its surroundings, sometimes it's very, very easy to do. Like, we can look at a fire and go, okay, well, the burning log is the reaction system and everything around it is its surroundings. Amazing. But sometimes it's more challenging, because if you're doing an aqueous reaction, if chemicals that are dissolved in water are reacting with one another, technically the water is part of the surroundings. Any thermometer you could stick into it is part of the surrounding. So it does get a little bit dicey, but you do just have to think about it a little bit. The main thing you want to be aware of is you and anybody, like scientists, are incapable of measuring a reaction system's temperature directly. It cannot be done, because the thermometer, or whatever you would use to measure that reaction system, is part of the surroundings. So again, you can only ever measure the surroundings of a system. So if I do a reaction, I stick a thermometer in the middle of that reaction and I detect a temperature decrease, that means that the surroundings are getting colder, not the system itself, which is a little weird to think about, but go with me. So let's look at this reaction system here. We have an aqueous reaction going on. So we have 2 of A plus B are going to yield A2B. All of those chemicals are aqueous, but I want you to take note of this right here. You are going to see this a little bit more going forward. And the reason that water is there positioned above the arrow is because it's present around the reaction system. It's necessary for the reaction to happen, but the water is not itself part of the reaction. So it is part of the surroundings. So with this reaction system, if we record a temperature decrease, that means that this thermometer is going to record that temperature is going down. So looking at this beaker, the parts of the system are literally the chemicals that are reacting. So that's all of these, the green and red, and then of course the products over here. That's it. There's nothing else in that picture that's part of the reaction system. The surroundings, on the other hand, are actually pretty numerous. The surroundings immediately would be the water molecules, which again are not part of that reaction. And remember, we define a system as the chemicals that are actually reacting. Another piece of the surroundings would be the beaker. Another piece of the surroundings would be the thermometer, and I'll abbreviate that. Another piece of the surroundings would be the air that surrounds the beaker. If somebody were holding that beaker, the person would be the part of that surroundings, etc., etc. The only thing that's part of the system would be your chemicals. So A, B, and A2B. Is that reaction endo or exo, and how do we know? Well, if we look at the information that we're given up here, we are told that a temperature decrease is recorded. What that means is the surroundings are losing energy or heat. If the surroundings lose energy or heat, that means that the reaction system have to be gaining energy or heat. And I'll just abbreviate heat as Q. So if our system is gaining energy or heat, that means that our Q value is positive and we have to be endothermic, specifically. If you have trouble identifying what's part of a system, what's part of the surroundings, where is energy going, etc., please ask me about it, because this entire unit is predicated upon your ability to understand where energy is going. So again, with this specific drawing, if I were to put arrows in here to indicate where the energy is moving, I'm going to put the arrows going towards the molecules themselves, from the water, from the thermometer, from everywhere else. Energy is going in because those molecules are absorbing that energy. And we know that that is happening because the surroundings, aka the thermometer, recorded a temperature decrease.